3, 2, 1. All right, welcome to yet another Math 2070 online video. All right, and as promised from our previous video, today we will be looking at an application of determinants, a very classic fact, a thing called Cramer's rule. So let's just jump into it and set it up, talk about what it is, and talk about how we can use it. All right, so in order to properly set up Cramer's rule, we got to introduce some notation. So if you have an n by n matrix and a vector b, we're going to let a sub k of b denote the matrix found by taking a and replacing its kth column with b. Now, if a times x is equal to b, then we know that multiplying a by the identity matrix, where the kth column has been replaced by x, will give us the matrix A, where the kth column has been replaced by b. Right, and it's pretty easy, hopefully, to see that. A good justification for this is recall that the product of two matrices, the kth column of this will be the matrix A times the jth column of this product will be the jth column of this times A, and whenever J is not equal to K, we just have the identity, so we'll just isolate the usual column of A, except when J is K, then we'll actually get B. So, not too shocking that this holds. Now, it's this matrix times this matrix, and as we just talked about, the determinant is multiplicative, so the determinant of this product has to equal the product of the determinants, as we see here. Missing a parenthesis right there, so let me go ahead and fix that. But here we find, all right, the determinant of a product is the product of the determinants. The determinant of this matrix, if you think about this for a moment, because we have the identity matrix going down here, if we were to do the cofactor expansion across the kth row, we will isolate the kth entry of the vector x, but then all of the zeros will delete everything out, and since the column is then going to get eliminated, well, the identity matrix has determinants out to 1, so we'll just pick up the x sub k, all right, the kth entry of x. All right, now this holds, and lo and behold, if we know our matrix A is invertible, then the kth entries of the vectors can be found. They are precisely the determinant of the kth entry of A, the determinant of the matrix A, where the kth column has been replaced by B, divided out by the determinant. This is Cramer's rule. So this gives us a way of solving AX equals B directly by using determinants. So note, we didn't compute the inverse of A. We simply just compute some determinants and we can solve for x. Let's see it in action. So let's say I have the system x1 plus 2x2 is 5, negative x1 plus x2 is 1. So here our coefficient matrix is 1, 2, negative 1, 1, and our right-hand side is 5, 1. So I'll create my matrix A1b, where I replace column 1 with the vector b, and A2b, where I replace column 2 with the vector b. I now compute the determinants of all of the ingredients, so I need the determinant of the matrix, the determinant of the matrix where I replaced column 1 with b, and the determinant of the matrix where I replaced column 2 with b. And note here I've got 3, 3, and 6, and from this I now can tell you that x1 needs to be the determinant of a1b divided by the determinant of a, which is 1, and x2 is the determinant of a2b divided by the determinant of a, which is 2. And you can check that that is indeed the solution to the system. So we have now a new way of solving systems using determinants explicitly with Cramer's rule. Now, when I learned Cramer's rule, my professor, Professor Fulton, said Cramer's rule is great for 2x2s. And that's it. So you can imagine, obviously, for 3x3s and beyond, there's a lot of determinants to compute, which can be very time-consuming. So not exactly a computationally viable strategy. While it's very nice and actually pretty quick for 2x2s, this is actually a pretty cool way of solving 2x2s, honestly. It doesn't exactly upscale very well. However, what Cramer's rule does provide to us is a true blue formula for the inverse of an n by n matrix. So we saw the formula for the inverse of a 2 by 2, and we saw the magic number, the 1 over AD minus BC. That's the determinant of a 2 by 2. So naturally, you would imagine that the formula for the inverse of a 3 by 3 and beyond, 1 over the determinant should be showing up somewhere. Hey, Cramer's rule had us 1 over the determinant. Maybe we can use it to get a formula for the inverse. Hey, exactly what I was just saying. All right, so recall that the kth column of A inverse is a vector x, so that A times it gets me the kth standard basis element. That makes sense, right? Because A times A inverse gives me the identity matrix, so the kth column of that would have to look like this. Cramer's rule tells me that A inverse is j kth entry, which would be x sub j here, has to be, and again, I'm missing a parenthesis. How dare I? Has to be the determinant of our matrix A, where the jth column has been replaced by the standard basis element, ek, divided by the determinant of A. And if you carefully look at this, if we were to cofactor expand on the jth column, note that what we'll pick up is the cofactor note starting with k and j instead. So it takes a little bit of like computational, a little looking at this to actually see that this is in fact what you get, the cofactor here. And that makes some sense, right? Because we're going down the jth column. The only entry that's non-zero is the kth one, so we're only going to pick up that. And note that then when you compute that determinant, yeah, you'll delete that column, and so then you'll pick up the determinant that's left over, so you'll just end up with the cofactor, but with the k-jth cofactor. All right, and now, ta-da, if I define the adjugate matrix to be the matrix that has these cofactors as their entries, this gives me an explicit formula for the inverse of a matrix. It's 1 over the determinant times the adjugate. And you can check for the 2 by 2 cases, this actually does give you the correct formula. And that's pretty neat. Now, the only tricky part with the adjugate is that the entries are put in kind of weird spots. So here we see we have row 1, column 1, but row n, column 1, instead the cofactor you're putting is the row 1, column n entry. So note the jkth entry here swapped which cofactor we're dealing with. So that's the only thing to keep in mind, and it gets a little tricky, but it's not the worst thing ever. So, hey, here we go. We have now an actual formula for the inverse of our matrix. So let's actually get it for our matrix A. So first things first, I'll save you the computation. This is a good pause the video and double check on your own that these numbers are right. The determinant of this matrix is 3, and its adjugate is as follows. And again, the way you compute this is by finding the cofactors. Remember, the cofactors is the plus and the minus of the minors. So, for example, this -7 I'm finding by deleting row 1, column 1, computing the determinant. Note the determinant is -7, and since I'm in the 1, 1 spot, it's positive, so we keep the -7. Now, here, this entry here, 2, note that this is the row 1, column, the row 2, column 1 entry. And the way we obtain this 2 is by going back to our matrix here and deleting row 1, column 2. Right, note you swap it, and then taking the determinant, note the determinant there is -2, and then remember that it's got to be the appropriate cofactor, which would then make it positive instead of negative. Likewise here, this -12, this is in row 1, column 2, so what we'll do is delete column, we'll delete row 2, column 1, compute that determinant. Note here you'll have 5 plus 7, giving me 12, but the spot we are in is where one of the cofactors will be negative, so it's -12. So you can go through and check and compute all of these correctly. So again, remember these are just the cofactors, but they're swapped. It's not the right row and column. You got to swap the rows and columns to get the cofactors. But anyway, with all of this, we can then scale this matrix by -1/3, and that gets me my formula for my inverse. Now, is this faster than setting up the augmented matrix and getting the reduced echelon form? I mean, not really, but it's good to know that there is a actual formula out there for the inverse for the interested individual. So, pretty cool. So, there you have it, and I might force you to do this on a problem list, so oh no. Well, hope you enjoy it. And with that, we'll say goodbye to determinants for. I mean, not the. We're never going to say goodbye to them, but with that, we've hit up the major things we want to touch on, and we'll start moving on to a new topic